We don't have a warm up today, no. No warm up. We're gonna jump into where we ended up at last time. Whoa, what's going on with my notes? Here we go. And then at the end, I have something for us to review. Okay? So prepare you guys for the test. Okay. Let's see. So we're doing section 4.7 still. A rational function. Let's call this part 2. And what we're going to focus on right now is something called vertical asymptotes. And this new thing we're going to call removable discontinuity. Which in the graph just means holes. You're going to identify where your graph's going to have holes. We're going to start with that first. A lot of factoring is going to happen. So let's play with some examples to kind of observe what's happening. So let's look at this rational function, x minus 3 over x squared plus x minus 2. Leave some room here. And then we're going to do g of x. It's going to be x minus 1 over x squared plus x minus 2. Okay. Okay. So notice they look almost exactly the same. Okay. It's just one has a minus 3 on top, one has a minus 1 on top. Turns out the graphs look totally different. Even with just that small change, we're going to see why. Okay. We're going to want to, let's say I asked you guys what the domain of this function is. Okay. You have a fraction. What is it about this fraction that you don't want to happen? You don't want the bottom to be equal to 0. So we need to see what makes the bottom equal to 0. But to do that, we're going to have to factor it first. That'll help out, okay? So I'm going to leave the top as x minus 3. And let's help me factor the bottom. What is it going to factor into? 2 things that multiply to -2 and add to 1?
To a negative 1 and then positive 2.
1 and positive 2. So like that?
Yeah.
So, yeah. Times -2 and then 2x minus 1x equals 1. 1x. Good. And this denominator is the same, so it factors the same way. Okay. What do you notice between this and this?
That one is cross out the x minus 1 on the denominator and then numerator, but the
Yeah.
first one can't because it was common.
Common term. Good. So here, this factors because it's the same on the top and the bottom.
Mhm.
So in reality, this reduces to what over what?
1 over x plus 2.
X plus 2. Beautiful. That, can we do something like that here?
No. No.
No, we cannot do something. Oh, right. Here, let's see if it lets me do it. Yeah, okay. So let's see, let's kind of observe what's going to happen with the graphs of these things. Oops, it's not showing anything. There we go. Can you guys see that? Okay. So here's the first one. By looking at it, can we, what's the domain in here then? What are we not allowed to plug in for x?
1 and
-2, right? 1 and -2 cannot be in the domain of this. So where does it seem to have vertical asymptotes? If I put x equals 1, and if I put x equals 2, Oh, sorry, -2, right? Let's color them the same. Notice that this graph has a vertical asymptote at these two x values that we're not allowed to plug in. Okay, so notice x cannot equal 1 and x cannot equal -2. Okay. Do you think the same thing will happen with the second graph? Let's see. So if I do the second graph, I only have a vertical asymptote at -2, and at 1, it seems to be okay. Okay. But here's where your knowledge beats the computer. Okay. So it only has one vertical asymptote. But look, if I go back and I look at the domain of this function, right? This factored into this. What would happen if I plug in 1 here to this function? Let's see. So we plug in 1, I'm gonna get 0 on the top, and then what do we get here? 0, 0. I still got 0 on the bottom there. So we still don't want that to happen. So is 1 in the domain? It's still not in the domain. Is 2 in the domain? -2 in the domain. Right. It still will make the bottom 0. Okay. So for this function, even though this term cancels, the original function can't plug in 1. So you still can't plug in 1, and you still can't plug in -2. So that's where these both agree. They both restrict those x values. But in this one, there's a vertical asymptote at -2. So something, if I'm not able to plug in 1, what do you think should be happening in the graph? Let's see. There's a freaking hole writing right there that you can't see. Okay. So the difference is this one has a vertical asymptote at 1, which is why it excludes it, versus the second one also excludes it, but there isn't a vertical asymptote. You just have a hole there. Okay. And so we notice that this guy here produced a hole at x equals 1. But this one that did not cancel off had a vertical asymptote at x equals -2.
Now, should there on the Desmos or the graph be like an open circle point? Have that undefined or?
There really is one. It's Desmos won't show it to you until you actually drag the point.
Okay.
Yeah. And so what ends up happening here, did anything cancel off? Nothing canceled, right? So that's why we still had 2 vertical asymptotes here. Here we had a vertical asymptote at x equals 1. And this guy didn't cancel, which gave us another vertical asymptote at x equals -2. Oh,
Why is it that that first graph has a third, like, third?
oh, you mean the graph itself?
Yeah,
Here, let's take a look at it. The third graph?
the first one, it has like a third, like.
Oh, this loop thing?
Yeah.
We're gonna talk about that, yeah, in a little bit, yeah. Yeah, because it's decreasing, right? But there's a vertical asymptote. It's decreasing, but there's a vertical asymptote, so we can't cross that vertical asymptote. So 2 things are gonna happen, okay? Could happen. It can either go like this and go down, or it goes back up. So towards the end of today, we're gonna have to do a sign chart again to help determine that. Okay? Yeah, because we won't know, right? Just we have to actually graph it. All right, yeah. Oh, like what? You mean like why this is not perfectly symmetrical, or why the?
Yes.
Let's see if, it's not perfectly symmetrical, right? No. It's a good question. Let me see.
It's because a word does not spot points, like the -5, -10.
Well, I think she's asking, like, if I look at it halfway, it's not like perfectly symmetrical like a parabola. Right? Hmm. I guess-
Line up with that too. And you see that like the way the spacing of 5.
Mhm.
is supposed to be like-
Well, like, I think, let's see, what's in between two, -2 and 1? Is it? Oh, -0.5? Yeah, it's definitely not symmetrical there. No, I mean, I guess if it was symmetric. Let me see, if it was symmetric. There would have to, I think there would have to be some kind of symmetry here. With these two functions. When we study transformation, at the end of it, there was a handout I gave you guys with even and odd functions. And I'm guessing, my guess is because the top is not an odd function and the bottom is an even function, that throws off the symmetry a little bit. I believe so. Let me see. Let me just put an x squared here. See what happens. Oh wait, we're looking at this one. Yeah, still, this one would be an odd function on top and an even function on the bottom. Let's say I made it even though, then the symmetry kicks in. I'm gonna go with that, but I'm sure there's other stuff happening there. Yeah,
Isn't the one on top?
it's neither. Mhm. And it's because of this thing where you're dividing kind of like an odd function and an even function.
Oh, I thought it, isn't it also because like x minus 3, x is just x to the first, and then 3 is like 3 to the 0th power. So when I do how.
Oh, yeah. You're actually correct. Yeah. Actually, yeah, you're right. This is neither and neither. I was just looking at the first power. You're right. You're right. But I'm thinking there is that symmetry because even in odds control that symmetry that happens. Okay. Yeah, good question. Okay. So let's see here. So notice that what ended up happening is from the beginning, these two x values are still restricted, right? They're not part of our domain. But what ended up happening, let me sure it's recording on the board, is if one of these denominator factors cancels out, we ended up getting a hole there, versus when it doesn't cancel out, we still get a vertical asymptote there. Okay. And so if instead, let's say on top of this, I had an x plus 2. Now these guys would cancel. So what do you think would happen at this x value? It's going to become a hole. Correct. Was that your guess? Yeah. Yeah. It's going to become a hole. And so that's how we're going to be able to determine when these x values that are not in our domain, whether we have a vertical asymptote there or whether we have a hole at those x values, is if this term will cancel. Okay. So let's do a quick sketch of the graph, just so that it's in your notes. So we had, let's see, 1, -2, and then we had 1 right here. Right now, we're just focusing on the vertical asymptote, okay? So the graphs had a vertical asymptote here, and then here, and the graphs look something like this. Versus the one over here. Only at -2, we had a vertical asymptote. And then the graph looked something like this, but then we noticed there was a hole there.
So I don't understand why there is a third, like.
Why
third-
there's three parts here?
Yeah,
One thing we were mentioning on Monday is that the vertical asymptote, your graph cannot cross there. Because if it crosses there, right, like let's say the graph went like this and it crossed right here, then it has a point there. Therefore, you were able to plug in one and get a Y value. But we saw that that can't happen here, otherwise you're gonna get zero in the denominator. So it forces it. It forces it. Because the domain only excludes these guys here. Like I gave you guys on the test. You would have to write the domain in interval notation. So it's anything less than -2. Union. Everything in between -2 and 1. Union, anything greater than 1. So your function needs to have input value of points for all these intervals. But because you're not allowed to cross the vertical asymptotes, that's what makes it split into 3 parts. Versus here, it's still technically split because of this hole, but just not through an asymptotic way. You're going to learn more about this in calculus. Okay. This right here, I got you. This right here is called a removable discontinuity. Because if I fill this hole, if I fill it, now my graph will be continuous there. It's connected. Versus when it breaks apart like this, there's no way to like connect it together. Okay?
Yeah.
Wait, you have a question?
For the one to the left, did you find the y-intercept by plugging 0?
Oh, this here?
Yeah.
No, I was just going off of the graph right now. We're gonna figure out where it crosses, but yes,
Okay.
you would plug in 0 for F. And then that would give you -3 over -2, which is what, 1.5?
Yeah.
But right now, I'm not worried about that. I just want you guys to focus on the vertical asymptote. So we have a hole here at x equaling 1. So here's the question. How do I know where the hole's at? Like, how do I know the coordinates of that hole? How do I know where it'll be, right?
If it also is on the top.
Well, more precisely, like, what are the actual, like, where is it located on the XY plane?
If you're just looking at.
If you're just looking at it, like, how would I find the X and Y coordinate of the points corresponding to that hole? Okay,
we should just put 1 into the Y place.
here?
Yeah.
That's what we did, but we know we can't do that because we get 0 to 0 because of this guy here. But notice that when it's canceled, I can plug it into this one.
Okay.
And actually, there's so much deep shit happening right now. I'm like getting giddy, but here, I want you guys, let's do something else to kind of help you here with this. I'm just gonna bring it down. Okay, this is the second one with the hole. Okay, we have a vertical asymptote right there, and there's a hole right at 1. Cool. Now let me write what we ended up getting. What was it when we canceled out the x minus 1? And I want you guys to notice the graph. What do you notice about the graph of this guy and the graph of G?
Same thing.
Exactly. This one does not have a hole there. Because on this function, I can't plug in 1. It's okay. It doesn't give me 0 on the bottom. But on the one on top, it's equivalent to the bottom function, except that for this one, I can't plug in. That one has a hole. So to find the coordinate of the hole, we're going to plug in 1 into its homie. We'll call it its homie, since they're homies and they're the same. Say it again. Oh, like when I factor it? Yeah, but after factoring, but then also after it cancels. After cancellation. So
So for the volume and negative 3 and negative 1.
Correct, because notice that this one still has a vertical asymptote at -2. Like they both agree on that part. It's just that one where they differ. Yeah. So to find the coordinates of that hole, what we can do is plug in 1 into this reduced version, and that'll give me the coordinates back. What happens if I plug in 1 right there? You're gonna get, I plug in 1, and what's the y value that I'll get? 1/3, and look, that's the point right there. That's located there, okay?
Why are we doing one again? Or do we do no?
So part of the homework is gonna give you this original rational function. You're gonna have to find the vertical asymptote, all this stuff that you're gonna need to do, and at the end, you're gonna need to graph it. You do all this algebra, and then you'll realize, oh, this canceled, so there has to be a hole at whatever makes this 0. But then when you're graphing, you need to know where that hole is at. So to find the hole, you're gonna plug in 1 into the result of what you got after you canceled.
You're plugging in wherever the word is.
Yeah, you're plugging in the x coordinate of where the hole is at. Yeah, so to find this hole, so you plug x equals 1 into the function you got after cancellation, which in this case is 1/x+2. So then I would get y is going to be 1/1+2, which gave you that third. So now you know your hole is going to be at 1, 1/3. So then you would draw your hole right there. Yeah. Okay. What we just discussed is really important in calc. Okay, when you guys study something called a limit. Okay, yeah.
So when you're like describing this point, like as a coordinate, would you do that, or would you just like put in 1 indeterminate?
Say that again, what do you mean?
Like the graph on Desna said indeterminate, and it's not a real, since there's a hole. Are you like identifying where the hole, like, because right now, if you look at that, it looks like the coordinate looks like there
Gotcha.
isn't a hole.
I agree, yeah, I see what you're saying. This is just so you know physically on a piece of paper where you make the hole. You, like, I don't want you to make the hole up here and then have the graph like
Yeah.
not agree with it, you get me? Like, it's just where it's located. But it's not a point on the original graph. Yeah.
Is it called a removable discontinuity? Because you can like remove it to find its coordinates.
It's called removable discontinuity because I can remove the discontinuity by simply filling the hole. Like, I can now make it connected. It's just the thing is that we haven't defined continuity. But in formal sense, it's the graph is connected. I can draw it without lifting my pencil. Versus here, from here to here, it's also discontinuous because I have to lift my pencil to then continue this graph. But there's no way I can make it continuous. I can't do something to it to make it continuous. So I can't remove the discontinuity.
But horizontal is asymptotes
Asymptotes.
are continuous.
Horizontal asymptotes are just gonna be horizontal lines.
Yeah, but like since you can go through them, does that mean it would be continuous?
We're gonna look at somewhere you could go through a horizontal asymptote. You just can't go through a vertical asymptote because of the domain issue. Okay.
So is there a domain for this one?
Yes, we still can't plug in this guy here, these two x values
So
to
would,
this function.
so would it have those or signs and all that?
It's, this domain is this domain of this function and this domain of this function. They both exclude -2 from part of the graph and 1, but in different ways.
Then how, when you see that domain, though, you know that they're graph completely different.
That's kind of the essence here is you have to factor it. If this factor that restricted this x value from your domain cancels, you end up with a hole there. versus an asymptote. If it doesn't cancel, then you have a vertical asymptote.
Okay, I see. So if they wouldn't cancel, then that would be where that always would be the line. And then it's on the other side, how it's on the bottom, and then that's where you get the parabola at the top. That's this.
That's correct.
Very significant.
And so right now, I'm gonna give you guys a practice problem. I don't want you to focus on the graph. I just want you to focus on where do you have a vertical asymptote versus where will you have a hole. That's all we're gonna focus on. So let's get to look. Shit, it's graphic. Okay, so factor the rational function to simplify it and determine any remember I'm calling them VAs for vertical asymptotes and removable discontinuities or holes. Discontinuities, Jesus, which graphically are just holes. And here's a function that I want you to do this for. X squared over 30, x squared minus 36. Hella factoring, okay? So you guys practice your factoring. Over x cubed minus 2x squared minus 24x. Try to factor it as much as you can. Both the top and the bottom will factor. Sure. All right, and then let's see. There you go. That part. Oh, okay. There we go. Okay.
When you plug in the X value, it'll end up as zero.
No, not quite, not quite. So what ends up happening is when you start plugging in X values that are really close to 1, this starts to become really close to 0.
Yeah. Which
And-
you don't.
And when you have a fraction with a really small denominator, it makes the overall fraction value really big. And so that's why the Y values are either going positively big or negatively big.
Yeah.
But here, when I plug in an X value very close to 1, whatever I plug in, like let's say I plug in 1.2. This will give me 0.2, but this will also give me 0.2, so these cancel. So this part that was getting close to 0 is gonna end up vanishing. So in reality, this takes control, which is why it behaves like this function instead.
No, I understand why it behaves like that function. I was just confused on the part that. Yeah, that one.
Yeah. No, you missed. Can I have you guys check your factoring? Check your factoring. Real quick, the plan.
Right, but X was 0, instead of 0 and find it X, which is the other. Right. But X doesn't matter.
So that would make it fun. And then the vertical is this 0, negative 1.
I don't know. No. Yeah, 0 doesn't cover.
Would it make it accurate? Or you have the 0 there? But if you had a 0, you make everything 0.
Right. Yeah, but then if they're-
There's a 0 in the numerator with that.
It makes the there, but that still counts.
Oh, would that just make it did I? And why?
We did more steps.
Oh.
Then. Either way, you said. Yeah. Yeah, I have 65.
It's the discontinuity that.
I just talked about.
From on step number 5.
But you gotta add it. I've added back. Come on.
I did it wrong, and then
The whole of that.
I did one again at first.
No. Let's see.
So 12 over 10.
Um,
I did the 6 plus 6.
And that's the. Which is kind of like, right, way. Okay. Hold on. One of the equations look like this, the denominator.
All right, guys, what did the top factor into?
So I plug in that too.
X, it's the difference of squares.
Oh.
X minus 6, X plus 6. Okay. Difference of squares factoring up here. 36 is a perfect square, it's 6 squared. For the bottom, what was your first step? Take that X out of there, make it not so intimidating. And then we ended up with X squared, 2x, 24, and then I believe this factor too, right? Let's see, X minus 6.
X minus 6.
X minus 6 and then X plus 4,
Yeah.
okay? And then
Just cross cancel X minus 6.
cross cancel this guy here. Okay? So what does this tell us now?
The whole is
The hole is right here. So we know we're gonna have a hole at X equals 6. And where do you have vertical asymptotes? Make sure you guys write at X equals -4, and what makes this 0 is X equaling 0. Okay, how can I find where the hole will be at?
Plug in the 6 to the.
Plug in the 6 into
The factor equation.
this guy, right? After I removed I removed the x minus 6. Yeah, so if I want to figure out where this happened, the whole, you would plug in 6 into this guy here, which would give you 6 plus 6 over 6 times 6 plus 4, which is what, 12?
Over
60.
6, oh shit, nice, which is 1/5. So you know that your whole is gonna be at 6 comma 1/5. That's where your whole is gonna be at. Okay. So we don't know where the graph is gonna be. We're gonna work on that in a little bit. But I know that I have a vertical asymptote at 1, 2, 3, 4. We know we have a vertical asymptote right here. I have one at 0. And then at 6, 1, 2, 3, 4, 5, 6, 1. We have a hole at 6, 1/5, like hella low right here. That's where your hole's gonna be. Okay. A lot of factoring, right? Questions? Maybe a question that someone asked you that you thought was a good question.
I bet it's possible to find like the negatives and positives, but is it also possible to find like the parent function so that you can grab it in the same way?
The parent function of this bad boy,
You know, of the pieces.
like where they go, that's where we're gonna work. That's our goal. Yeah. It'll be hard to know where it twists,
Sure.
like exactly where that twist happens. We won't know that yet. You'll need calculus to know where that happens.
Mhm.
So we'll just kind of approximate it. Yeah.
Is this the end of the rational function?
No, this is half of it.
If you
So-
will find the vertex.
We need it, yeah, we need to know where, now we need to know where you're gonna cross the x-axis, the x-intercepts, and where you have a y-intercept, if you have one. Okay? Right.
And then why are why do we know that they're the vertical asymptotes and not the zeros?
So Brian asked me a similar question. Let me answer that with these two, okay? So here, if I plug in 1, the top, if I plug in values very close to 1, like 1.2, 1.01, you'll get some number on the top. But then this factor forces this to start getting close to 0. Starts getting really, really small, which will force the whole denominator to get really, really small. Okay. And so let's say you guys, let me just write it over here. Let's say, let's plug in let's plug in to this guy here, plug in 1.01, like really, really close to 1, right? So I'm gonna get 1.01 minus 3 over 1.01 minus 1, and then 1.01 plus 2. Help me out here. What is that going to give me?
Wait, 1.9. Yeah, negative 1.9.
199 or 299? 199. Thank you. Over
0 times 3.01.
301, right? What happens when I multiply 0.01? Need somebody with a calculator?
That just move the denominator? No, would it? Yeah, would it move the denominator 2 spots?
I think it moves it 2 spots.
So 0.003.
Like that?
Yeah.
Yeah. But notice that because this guy's small, this number's small, it's gonna force this one to also get small as well, right? Now, someone, again, with the calculator, go ahead and compute, what is this here?
Something large.
Or here, I'll do it on Desmos. What is it? Let me see, 1.99 by, and what is it, over 0.0301? Yeah, it's negative 66. Something. And so notice that it's getting, it's a big negative Y value, right? 1.01 was like around right here, and notice that this graph goes down like this, right? So the closer I get to 1, like the closer this number is getting closer to 1 from the right, the overall fraction is going to end up becoming a really big negative value, which is why it's forcing it to go down, which is why you're getting this asymptotic behavior there. Versus if I plugged in the same number here, I'm running out of board space, I apologize. I'm going to do 1.01 minus 1 over 1.01 minus 1, 1.01 plus 2. But notice what happens with this number. You're going to get, what's that, just 0.01 over 0.01 times 2.01. But what happens with this number and this number? It cancels out. And so the smallness of it is gone now. And so that's why you're not getting an asymptotic behavior, because it's not going to affect this number getting really small. So then it just behaves like this function instead. And so that's why the two graphs were kind of agreeing there, except that this one did not have a hole and this one did.
I guess it's wondering what, I know that you, on the test, you'll kind of give us categories of like finding zeros. But
Mhm.
like, if we were just given something that says fx equal x minus 3 over x minus 1 equals 2, how do we know that we're not just setting the bottom to zeros and making the 0 1 and negative 2?
Yeah, so you would have to first find what makes it 0 to start with, but then if that factor, that linear factor cancels out, that's what's causing the hole to happen.
Okay.
When it doesn't cancel out, it forces this kind of asymptotic behavior to behave, and that's why you end up with the vertical asymptotic effect. Yeah. Someone else had a question? Reggie.
So if it cancels out, you don't get a vertical asymptote.
Correct.
But if it does, you get a vertical.
If it cancels
Cancels
out,
out.
you don't have a vertical
Yeah,
asymptote.
but if it
If it does
doesn't-
cancel,
does cancel, you have a vertical.
you have a hole.
Oh, you have, okay, okay.
All right. Good questions, I like them. Okay, so this is the focus on vertical asymptotes. Let's do horizontal asymptotes and then we'll take a break, okay? So this on this part here. Still recording, I hope it's still recording. Yeah, it's still recording. Okay, so let's see. So now let's focus on horizontal asymptotes. And I have a little handout for this one. And actually, before I pass out the handout, let me show you guys what we're going to discuss real quick. Came prepped and ready, so let's see. Okay. When we were doing polynomials and we were looking at the tails of the polynomial, the end behavior, what was it about the polynomial that we were using to help you determine the end behavior? The leading coefficient, or just the leading term in general, right? We're seeing if its degree was odd and if the coefficient was positive or negative. That was telling us how the tails behaved. So it turns out for a rational function, because it's being divided by two polynomials, what's going to help us determine the end behavior are its leading terms also. Okay, because those are the ones that will overpower the y values of the function. So let me pass out this handout so you guys can see what I mean. Let's see one. There's this part that says horizontal asymptote rules and net behavior, and then there's a worksheet we're gonna do later on. But just look at this side right there. That's about it. There's 6 of you guys here. And then I'll just put these in. Grandma, pass it back.
It's the balloons or last lesson, for things that.
Yeah. Okay, so let's see. Oh, wait, does someone have an extra? Okay, so it says. If the degree of the denominator is greater than the degree of the numerator. It's telling us that we're supposed to have a horizontal asymptote at y equals 0. So, which of these, the first one, second, or third, satisfies case 1? What's the degree of the top of the numerator here? What is it? 2, the highest exponent. What's the degree of the bottom? 3. So we have that the denominator has a higher degree than the numerator. Now, why is it that we're going to have a horizontal asymptote at y equals 0? Remember, the tails look at what happens as x goes to infinity or negative infinity. So as I start plugging in bigger and bigger values, like 100, what's essentially happening is that 100 is being plugged in here, and I'm getting 100 squared. I subtract 36 to it, but 100 squared is way bigger than 36. So essentially it's close to 100 squared. The bottom is 100 cubed minus the rest of the polynomial. But the 100 cubed is what overpowers the overall essence of the denominator. So I have something that's like 100 squared on top and 100 cubed on the bottom. So the overall fraction value is actually really small. So notice what happens to the y values as x keeps getting bigger. Oh, damn it, I hate when it does that. Let me see if it lets me do it. Nope. Notice that they're getting smaller and smaller and smaller and smaller. And when you look at the graph, that's exactly what's happening. As x goes to positive infinity, the y values get smaller and smaller and smaller. That's because the denominator gets really, really big. Okay. Let me see. How do I say this to my calc students? So if your denominator overpowers the numerator, if your denominator gets really, really big and it overpowers it, the overall fraction gets really, really small. Okay. And so that's why case 1 ends up having always a horizontal asymptote at y equals 0, because the y values get really small and approach 0. Okay. Case number 2 says the degree of the denominator is equal to the degree of the numerator. Uh-oh, I made a typo. That should say x squared. 6x squared plus 1, the middle one. Sorry. Can you guys fix that? The numerator should say 6x squared. Whoops, my bad. Sorry. So here, let's keep making x bigger. So I plug in 10. X keeps getting bigger. Now, what does it seem to be approaching? It seems to be approaching the y value 3. And that's because the numerator's leading term overpowers the whole numerator value. And this leading term overpowers the whole value of the denominator. So think about it. Think of having this ending up to look like this: 6x squared over 2x squared. As x gets really big, these terms get left behind, and the leading terms end up dominating the value of the function. But what happens if the x squared, if the degrees are the same? What happens to the x's? They cancel. So what you end up approaching are the leading coefficients of the top over the leading coefficients of the bottom, which is what's 6 divided by 2? Which is why this is approaching where to go. Oh, yeah, I fucked with the function. Yeah, that's why this keeps approaching 3. What do you think will happen if I change this to an 8? It's going to be approaching 4. Sorry. It's going to be approaching 4. Yeah, notice it's approaching 4. Sorry, I wasn't showing the right graph. See, this is the one we were looking at, but if I change this to an 8, now it's going to be approaching the y value 4. Okay, here's an example where the graph can cross the horizontal asymptote. That's okay because it doesn't affect any of the domain stuff. All you care about is the end behavior. So notice that it like crosses it, but then eventually it like crosses it, but then it kind of gravitates back towards the asymptote. Okay. So this is an example of one where it crosses the it's okay for the graph to cross the horizontal asymptote, just not a vertical. Yeah. Mm-hmm. Yeah, you can plug in 4 there. I think for the original one, look, it like hella crosses it, but then eventually it gravitates back towards it. Okay, same thing with this one. It crosses it, but in this case it doesn't, but it can. It can. Yeah. All right. So what case 2 is trying to say is if the degrees of the top and the bottom are the same, your horizontal asymptote is going to happen at the leading coefficient of the top divided by the leading coefficient of the bottom. Okay, Logan. We're gonna see in a little bit. We're gonna kind of do a sign chart to help us decide. Oh, and it ends up happening that the graph will have to cross it. So that's where all that's gonna come in. Yeah, I mean, right now it's gonna be let me see here. We're gonna look at the asymptotes and any x-intercepts. We'll see what the example that we do later on. Yeah, I did x cubed. Yeah, sorry guys. Cross out the graph. I effed up because I wrote an x cubed there. Dang it. Yeah, I think it's look. Oh my god. 2x squared minus 2x minus 5, right? Yeah, I'm just gonna have to. Damn it. I apologize for that. Okay, case 3 says the denominator's degree is smaller than the degree of the numerator. So let's look at that graph. Here, notice the tails don't gravitate towards anything. They just shoot to infinity and negative infinity. So in that case, there is no horizontal asymptote. Okay? Okay, so let's see. So how are we going to use all this stuff? Let's do an example now where we're kind of being asked to find everything. Actually, let's take a break and then we'll do it. Let's take a break, take a break. You guys look tired. Let's come back at 2 o'clock. Come back. Listen. No spoilers yet.
Professor?
Yeah.
I solved it.
You what?
I saw the equation before you left.
Oh, sweet, I'm sorry. It's the 4 divided by 3. Good, and we got. Numbers, and plug in the accordion. Okay. So let's do, we're gonna put all of it together, okay? What we did on Monday. And what we just learned on these asymptotes and removable discontinuities. So we're gonna refer to our handout to help you determine the vertical asymptote. So you're gonna use it for these following problems. So let's say we're asked to graph the rational function f of x equals 3x plus 6 over x squared minus x minus 6. Okay. So let's practice what we did first. Let's or actually let's practice what we just did right now with the horizontal asymptotes. So we're gonna have to find the horizontal asymptotes, vertical asymptotes, y-intercepts, and the x-intercepts. Okay? So it's kind of a lot of stuff. So let's see, let's organize this a little bit. Let's do horizontal asymptotes first. So here we're going to use the function that we have. And let's see, we got to determine which case do we have, case 1, 2, or 3, by looking at the leading terms of these guys. So what's the degree of your numerator? This has degree 1 and the bottom has degree 2. So what case do we have? We have case 1. So that's all we have to do. We just have to look at the degrees. Okay, so this tells us that you're going to have a horizontal asymptote at x equals 0, y equals 0. By looking at the degrees. Okay. And that's it. That's the only asymptote we're going to have. So now we're going to move on to vertical asymptotes. Wait, hold on. Is that okay? What does this mean? That means that the tails, as x gets really big, what are the tails going to approach? 0. They're going to approach y equals 0. Let's review that notation. So as x goes to infinity, f of x needs to go to 0. And as x goes to negative infinity, also, as I go this way, the graph needs to approach y equals 0. Yeah.
How do you get the 0 again?
We use the degree of your polynomial on the top. This had degree 1. And look at the degree of the bottom one. And so we have the degree of the denominator. In this case, it's bigger than the degree of the numerator.
Okay.
And that was case 1. And so this tells us that this will have to be our horizontal asymptote. What if on the top, this was degree 2? Say this was degree 2. What would be your horizontal asymptote? 2 or 1?
Yeah.
It would be what's the leading coefficient of this guy here? 3. What's the leading coefficient of the bottom?
1.
So it'd be 3 over 1, which is 3. If the degrees were the same. if the degrees were the same, okay? We'll do some, yeah, we'll practice more. Okay, now we're gonna see if we have a vertical asymptote or a hole, okay? So what we did in the beginning of class, so we got, 3x plus 6 over x squared. You don't have to rewrite it, I'm just rewriting it. And we got a factor. That's right, so you want to start training your eye, right? Notice that both of these are multiples of 3, so you can take out a 3. And you're left with
Plus 2.
x plus 2. Here you have, remember what we were calling this? It started with a t. When there's 3 terms, trinomial. So when you see a trinomial, you want to think of a different type of factor. You want to see what 2 terms can this factor into?
That's plus 2.
X plus 2. Is there cancellation?
Yep.
There's cancellation, so there's going to be holes happening. So once this cancels, I end up with 3 over x minus 3. What does this part that did not cancel tell us must happen at x equals 3? This tells us that we have a vertical asymptote at x equals 3, while this one tells you you're going to have a hole at x equals -2.
It's -2 because it's the opposite.
It's what makes this bottom guy 0, correct? So which ends up being opposite. All right, so far we have our horizontal asymptote. We have our vertical asymptote. We have our hole that we know needs to happen.
We want to plug in our hole.
Oh, sure, yeah, let's plug it in. Plug in, what do I plug it into? Into this bad boy, yeah. So we plug in 3 over -2 plus or minus 3, which is what? 3 over -5. That's -0.6.
Yeah.
3 divided by 5.
The answer is 0.6.
There we go. Okay, so there's gonna be a hole. What's the corner of my hole?
-2. 3 over
-6, good. That's where you're gonna have your hole. Okay, so I have these 2 pieces of information. Now we gotta do the asymptote, the intercepts. Okay, which one do you guys want to do first? We'll do the X one, okay. So let's do the x-intercepts first. What do I need to do to my function to start that?
Equal it to 0.
Equal it to 0, so we're gonna set it equal to 0. So 3x plus 6 over. Is it cool? Actually, yeah, whatever, let's do this. We already factored it, right?
Yeah.
We already did all the factoring. And then let me stop right here. Okay, what would you guys do from here?
Put it back in the right one.
Write it in factor form? Okay. So I'd get that, and then it was, what was it? It was
X subtract 3 and X plus.
okay, and then from there, what would you guys do? Cancel out the x plus 2s. Okay, and then from here, what would we do? Both sides by,
X subtract.
beautiful. Here, now this will cancel with this one, which leaves you with 3, and then this becomes 0. Uh-oh.
It's not supposed to be 1.
No, it's okay. But what does that algebra tell you?
Never crosses it.
It doesn't cross the.
Yeah, there are no x-intercepts. So this tells you that there are no x-intercepts. So it'll never cross the x-axis.
Don't we know that already from the beginning? Though? The horizontal asymptote is that y equals 0.
Yeah.
So there's no point in doing the one x and just.
Well, it's like.
Oh, you mean from this?
Yeah.
Well, remember, we don't know, the graph can do some funky crossing stuff. This just tells you what happens at the end of the tails, but not like what happens in the center of the graph.
You're saying like if there was like a problem. What is in this case, it wouldn't be because there's only one, but
I think what he was saying is, and correct me if I'm wrong, Eric, is that he knows the graph has to like approach the asymptote, so it won't cross it. But what we were saying is sometimes you do cross a horizontal asymptote. Yeah, but in this case, because the horizontal asymptote is the x-axis, this shows you that it actually will not cross the horizontal asymptote.
So in other words, this is just.
or no.
Because there are no x, yeah, because if it, so here's my my horizontal asymptote, it's right here, right?
Well, because like on the second one for this one, you can see that it like goes over, so you're basically saying it wouldn't be able to do that for this one.
Exactly.
Would you say that this was like a way of proving that it doesn't happen?
In this particular example, yes, it is a way of proving that you know it'll never cross the
Yeah,
horizontal.
so that you don't mess up.
Exactly, yeah. All right, what's left?
One.
The y-intercept, right? The easy one.
This problem.
Let's plug it in. Let's plug in 0 into your function. So plug in 0 here. 3 times 0 plus 6. And then 0 squared minus 0 minus 6. Which gives me 6 over negative 6. Which is
One.
negative 1. So you know you're going to have a y-intercept right there. At 0, comma negative 1. Okay. Eric, yeah.
And you could have also, instead of using like the original function, we would have gave you the same answer if you used the factor.
Completely, yeah. Yeah, you could have used this factor one right here.
You can just use the factor one.
Mhm.
Which is X over real X.
You can use it in this case because the whole doesn't happen at x equals 0. If the whole was to happen at x equals 0, you gotta be careful. It might cross the y-axis, but in reality, it goes through it, but really there's a hole right there. Yeah, just be careful. That's what's gonna be tricky about these, is like, you're gonna do all these things, but you kind of have to see the big picture at the end of it.
So if the whole were to happen and x equals 0, and it would like, should there anything in the form isn't there if you use the factor form?
Yeah, like, let me give you an example what I mean. So, like, you might have some funky business where it goes like this. Like that. Yeah. But if this was to happen, you would see that you couldn't even plug in 0 because 0 wouldn't be in the domain. So those like little flags would be like, whoa, something funky's happening. Okay, so let's see. So once you guys have all your pieces of all the information, what you're gonna want to do is do a big, large XY coordinate plane and start kind of putting everything together. So we know there's a horizontal asymptote here. So I'm gonna go ahead and draw my horizontal asymptote at y equals 0. So here's my VA, or my HA here, my horizontal asymptote. And then we have a vertical asymptote at 3. So then 1, 2, 3. I'm gonna draw that. You're gonna draw a nice vertical asymptote like this. And what else do we know? And we have a hole at x equals -2 with a really small negative y value. So I'm gonna go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So at -2, I know -2. Oh, here, let me write the -2 on top. -2, and what is it? -0.6. So a little bit more than halfway down. There's a hole right there. Okay. Any x-intercepts?
No.
No. Where do you have to cross the y-axis?
0, negative 1.
-1. So you know your graph has to cross right here. All right. The nasty part or the annoying part is that we're still gonna have to use the function and plug in some x values, unfortunately. Okay, to see if it'll be positive or negative, to kind of help you gauge where it'll be at.
Wouldn't we know it can't be positive because it doesn't cross the other?
So there'll be some parts where you should be able to like conclude from what the pieces you're given. You know the graph has to cross here, right? So can there be any graph up here? No, because if there is part of like if there is graph up here, at some point it has to go through here. But then it'll cross the x-axis, which can't happen. So we know that on this side of the vertical asymptote, the graph has to be below. So start at a point that you know is there, this guy. And as you go towards this vertical asymptote, as you approach 3 from the left, in the graph will either have to go towards negative infinity or positive infinity. But can it go towards positive infinity?
No.
Why not? Can't cross the x-axis, so therefore it has to go towards negative infinity. So now we know the graph. How exactly it does it? We don't have enough information, right? Like I don't know if it'll go like
Just know
this.
that it just-
I just know that it has to do
Go down.
shoot down that way. Yeah. This is a hole on the graph. So the graph goes through it, right?
Yeah.
Like it has to kind of approach it like that.
Yeah.
So I know the graph will go like this.
But does it also go to the X?
Yeah, so will it do something like that? Or does it have to stay below?
It has to stay.
It has to stay below. And as x goes towards negative infinity, the graph needs to approach 0.
Zero.
So we know it has to get close to the x-axis without touching it. Okay, so it's a puzzle, like a puzzle. You gotta kind of put the pieces together. Then there are the x values on the right side of 3. We don't know anything about that. So here's where you have to actually plug in some points and just kind of get a feel for it. So to figure out if the graph's on top here or here, whatever it is, can it cross the x-axis and do some funky business?
No.
No, so it's either gonna have to be on the top or the bottom. So use a test point to help you figure that out. So I'm gonna use a test point.
Wouldn't it have to go up because we know it has to reach for the positive infinity?
This right here,
Oh, wait, no, that's X. Okay, no, I get what you're
this is x, this is
Yeah.
x, yeah, so as x goes this way, we know the graph, if it's on the top, it has to approach
Yeah.
from the top or from the bottom, we just don't know which one it's at,
saying.
okay? So we have to use some test values here, pick one from me. 4, okay? You plug in 4, so you're gonna plug in 4 into your function. Plug in 4, I did that for you already though, but that is part of the annoying part of this problem. It's 3. So that means that your graph has to pass through the point 4, 3. It has to pass through that point. So what does that tell you about the graph? Does it go, like, what can I do as I go this way?
Go up.
It has to approach, it can't go down, right? Because then it crosses the x-axis. So it's gonna have to go up. And this way, does it go up as well?
No, it's down.
It has to approach the asymptote.
Into
That's
zero.
part of it. That's the beauty of the end behavior here, that it gravitates towards it. So I know it can't shoot up, so it must go down like that. Kind of get close to it like that. Question? No. So yeah, so here we had to use a test point to help you. Whew, it's a lot. So you'll start with this foundation, these foundational pieces. And then from there, try to figure out as much as you can. When you get to a point where you can't figure anything out, you're gonna need to use test points, okay? Yes. This one here is, this test point here. 4, 3. Plug in x equaling 4 and into the function. Bobby helped me out here, plugged it into the function and he got 3. They got 3, okay? Okay, so now in the handout I gave you, there are 3 rational functions. Obviously, there's not enough room. Okay, so let me have you guys try at least, what time is it? At least 2 of them. At least 2 of them. Try it out. Yeah, right up, and then I'll do this. Just marking some stuff. I'll leave this on the board. Let me just check something real quick. Boop, 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 boop. Yeah. You check that one. Yeah.
You have office hours tomorrow.
I have them tomorrow, 11 to 12, and then I have in Mesa.
Oh, you're gonna see me.
So on the separate sheet of paper, guys, you guys are gonna have to do the following because there's not enough room. Yeah. Guys, for number 1,
Oh.
for number 1, the numerator just has a 4, right?
Yeah.
The numerator just has a 4. What degree would that be? It would be degree 0 when there's no x. It's just degree 0.
This is my house.
What's up?
Did you guys see it? Like, 3 and 49? Like, the
Where?
out wide is it?
That was, we used, in the back here, we're using to determine which case we have, to see where the horizontal asymptote is.
Oh,
And because the degree of the top
Yeah.
was 1 and the degree of the bottom,
Mm.
we got that the degree of the denominator was bigger than the degree of the numerator.
okay. So for one, if the degree is 0, then it's less than.
But remember, it compares it compares the denominator to the numerator, not the other way around.
Oh,
So the degree of the bottom is greater than the degree of the top. So the wider, yeah, the wider.
Thank you.
Horizontal asymptote. By the way, this is the last stuff that will be on the test, okay? So you maybe want to copy down this table here on your cheat sheet with the cases. Okay?
So. Notice that this test compares the bottom with the numerator with the denominator. So here is the what can tell the bottom compared to the. So which of these three tells you in practice? Denominator means. No.
So you got the setup right,
Yeah,
you know it's gonna factor that way.
and then I have to have two numbers that could equal this and this.
Two numbers that are going to, when there's a 1 here,
Mhm.
and this is just a 1, yes.
Okay,
You wanna find two numbers that multiply, because see how when you FOIL,
yeah,
you end up multiplying this two,
yeah,
that multiply to -10, but add to +3.
Okay,
it's interesting.
where's the?
The y-intercept,
The x-intercept.
x-intercept,
Where's it?
well, it's so you see how
Both sides by that, and that would cancel out with 0.
that would, if you multiply both sides like this,
So
right?
get 0 equals 4, so that would work.
Exactly. So it'd be like this scenario here.
Yes.
Yeah, yeah. Okay, guys, can I have you just check with your classmates, kind of compare your work real fast? Just to make sure you're on the right track?
No, you're all good. I was written down wrong.
Oh, yeah, but you.
Yeah. Let's see, did you get it? There you go. Because notice if you multiply x and x,
Yeah.
multiply these two, the x over -2, -2,
Yeah.
plus 5x, gives you +3x. And then 5
Thank you.
Okay, good, yeah, the more you do it.
You know, the y-intercept is below the x, would it look like, it would be like a linear picture.
Well, yeah.
Well, do we need to know? Wait.
No.
Why is it?
No.
Since there's nothing that cancels now,
Mhm,
that means there's no hole,
correct.
so there's nothing else you can do.
There's no holes, but there are two. So it doesn't cancel,
There's 2 points.
there are two vertical asymptotes.
Oh,
So it's gonna be two of these
okay.
at those x values. At the one.
So this would just be x equals.
You're.
I just wrote it.
That x equals 2 is where you have a vertical asymptote, but this one also didn't cancel.
So then it'll be also a 5.
It's -5.
-5, okay.
Correct.
If there are two vertical asymptotes, is there a problem?
Because if the.
As long as you know for sure your graph doesn't cross the x-axis,
It's gonna be.
Okay.
because it might, right? So like if I,
If the problem, does that have to be, up or down?
And the one that you're doing, I think it looks like that.
Yeah.
So. There's gonna be a vertical axis up here, vertical axis up here, but then the y-intercept
It's gonna tell you.
tells you where will it be up here or will it be down here?
Oh, if it's down there, it has to be.
Yeah. it's gonna-
If it's down here and it's facing up, then it'll have to cross the x-axis.
Okay. Well, that's so if there is a.
If there's no x-intercept. Oh, well, you're first gonna check this.
Okay.
If you get that there are no x-intercepts,
There's no-
then you know that if your y-intercept is down here, for example, the graph can't have a parabola going up or a U shape, it has to go down. If the y-intercept's up here,
It still has to go.
correct, correct.
We don't have the fine, you know how he has the 3 over x subtract 3? We don't have that for number 1.
On the week 8 Canvas module are the solutions to this, okay? On the week 8 Canvas module. We'll go ahead and check. if you want.
Which is the factor. Which is
Let me
the,
just share.
okay,
It's easier.
so.
Yeah, so you can,
Plug in.
yeah, well, for Y and C plug. No. So, I mean, you know, when it's for the x-intercept, you
Yeah.
take this equal to 0.
0, yeah.
It's for the Y and C. plug 0.
0.
Uh-huh.
Oh,
Gotcha, like a reference, right?
yeah. Professor. So since there's nothing else in the can I multiply negative, I mean, x subtract 2 from this?
You can actually do more than that. You can subtract, you can multiply all of it on both
Both
sides. Yeah.
Oh, and then cross.
Yeah.
Yeah.
No.
There's 3 parts of it. You can do one. There's the middle part, you can do the acid parts. And then there's something that's not as one or something that's-
So when you multiply x plus 5 minus 2 here, you get the same.
Oh, oh, so bring it here, so then here would be x plus 5, subtract, I mean, this equals 4, instead of 4.
I'm not clear. You'll multiply this side like that, but since it's zero.
Is 0.
Yes. it's on place. So, yeah, so 4.
4.
But it's in that case, did you have to do that right now? So it's
The asymptote controls the end behavior.
But like the approach is.
You should know how to do it. Yeah, you should know how to write it.
What?
You're filling, it's okay, you're filling that calculus pain, because your teacher's gonna have you do that shit over and over and over and over.
Okay, one back. There's no x.
Good.
Why intercept? We just plug in 0.
Guys, my solutions are wrong, okay? I'm gonna have to update them. Yeah, I apologize, it happens, you know? It's just, I try to do them really fast. And it bit me in the butt.
that happens.
Yeah, I'm human, just like you guys. I'm not Chat GPT, so,
Oh.
Which makes me think too.
but yeah, it does.
Actually did say that.
Plus 3.
The girl tried to use it, and then she got fired. I was like,
You don't know how. It's a good heads up.
yeah. She just copied and pasted. it.
How would
She
I-
didn't- oh, She didn't even try. That's so dumb.
See.
Wait, can I ask? I think I'm doing this wrong. For the wines or something?
On the first step.
Yeah.
Yeah.
You get -2 or
I got -4/10, so that's the same thing.
Yeah, but mine is just simplified.
Yeah.
Okay, so it just be
So, like-
0, comma, negative. Watch me forget this person. So bad.
Any holes?
Okay, now we drop it. I don't like that.
I don't like mine.
Me and you both.
Oh,
Wayne. People who are down with math are so lucky.
You've got the mouth.
I love numbers. Really? You love numbers. Oh my God, slay. So much. Like you've got engineering industry. And then
Is there an
Oh,
X
maybe,
right?
maybe.
My brother wants to know that's like that. So you put it through.
it just makes me an ego. I'm like, okay, like, it could be too actually true. I don't want to.
I just can't get the motivation. Because, like, it's hard to like apply it to practical. So I can't get the actual.
Like math, it's taking me so much time. Like I'm trying to subject that I need it and trying to enjoy it, so I can learn it. Because I need to learn it.
So it's easier for me to learn like.
Oh,
Like,
right. Yeah.
like that and so like.
About 3 more minutes left.
It's easier to.
Right. But then it's like math is like, what the fuck? And then.
And like, oh, you can apply it this way, and I'm like, when am I ever gonna do this?
Right, exactly. And then it's like, actually, you end up using math in law and stuff, like when you're a lawyer,
Yes.
but everything else not one.
They just so that it's like you're rich. No, I mean, it's here, so you're lost in the jungle. With can't find. Yeah, it's hard. It's true. Yeah, you wanna know.
It is true, okay. So number one, it doesn't cross the X
Oh,
axis.
shit. No.
So.
I don't think so.
What? It's vertical.
The horizontal.
I crossed the line.
Yeah. And then, the y-intercept is negative, I mean, 2 over 5.
Yeah.
I use this right here. So if I were to get.
Little bit.
Okay, let's go do one now.
Right here.
Yeah.
Guys, for number one. For number one, most people got this part. You got the y-intercept. What is it, like -2 fits?
Yeah,
Let's say it's like right here.
uh-huh,
Yes.
And there are no x-intercepts, so you're concluding that it goes like that.
yeah,
Are you done?
no. 'cause it's
No. There's more to the graph. There is this side of the vertical asymptote that you have to figure out. And there's this side of the asymptote.
You got your test.
So if there are 2 vertical asymptotes, there are 3 parts of the graph. Okay, there's 1 vertical asymptote, there are 2 parts of the graph. If there's 5 vertical asymptotes, I won't do that to you, but if there's 5 vertical asymptotes, there's gonna be 1, 2, 3, 4, 5, 6 parts of the graph. I won't do that to you.
Can we see an example though? Just to stare us in the shade.
Sure.
No.
Yeah. Oh, God.
And then would that put like a bunch of the parabolas in the middle and then there's things on the side?
Well, you would use test points to help you figure that out. There's no x-intercept because you multiply the denominator, you get 0 equals 1. But yeah, that's a crazy nasty that I will not do to you example. Okay, guys. We're gonna do a little review for the exam. So let me have you guys put your stuff away. We're gonna move on here.
My brain is fried.
What a better way to prepare for an exam than with a pop quiz exam, right?
No. I can't.
Yes. 100%. 100%.
It's for me to forget.
Without any grades hurting you though.
Oh, okay.
Yeah.
Can't afford it.
No, you know, like the actual exam is now, I.
No, but what it will do, it'll tell you, oh, I really need to study this because I'm really lost. That's what it really,
I don't like that. That's not.
well, and then, yeah, so I'll give you guys some time. I'll give you guys some time to work on a few.
Okay.
Okay,
We
let's
ask
see.
questions.
There are 6 problems. You probably won't finish it. It's okay. 1, 2, 3, 4, 5, 6.
We can do this and the review guide, this would be good for the test.
And a couple more, maybe things from the homework, and problem set stuff, yeah.
Yeah, Monday?
Don't say that.
All right, guys, so go ahead. When you get it, I want you guys to try it without any notes, without anything. Actually, you can use your note, it's okay. In your note sheet, sure.
Okay, the first step.
You're welcome to use your notes to try these out. But do not talk to anyone else, please. All right, guys, try it out. You're welcome to use your notes. No internet. Like no Googling or ChatGPT or whatever the hell. So many things now. Math, Excel, civil lab, well, All right.